Okay, hello everyone, I'm Charlie, and today I'm going to be talking about minimizing entropy to discover good solutions to recurrent mixed integer program. So in collaboration with Emma Frejinger and Jean-Francois Cordeau from University of Montreal. So the plan today, I'm going to be talking about our case study, so the LAP, our methodology, so how we're using entropy to make better decisions, some experimental results, and we'll conclude with some future works. So I'm going to be talking a bit about the LAP, the Locomotive assignment problem from Canadian National Railway Company. So the problem is that we have some kind of payload to transport from one station to the other. And the question we want to answer is figuring out the assignment of locomotives to minimize overall cost. And this is an interesting problem to use ML because it has a lot of data and it's a recurring problem that needs to be solved every day and every week. So the problem has two main types of constraints. Assignment of constants to a train, which are binary variable, and we have flow conservation constraints, which are continuous. And the main idea here is that if we can predict the assignment, the binary variable, then we can significantly speed up the solution time. And so we do not make that many assumption about the MIP formulation, but we do make one important assumption, which is that there is one special ordered set of type 1, which are a set of variables at most, one of which can take a non-zero value, all others being 0. So one way to think about it is that there is some kind of classification within the MIP. And so a set of classes K, a set of objects V, and we model that assignment using a binary variable XVK. And so before we go into much details, I want to place our work on a specificity versus learning grid. So at the bottom left, low specificity and low learning, we have Cplex and Gurobi, which will be our baseline in our case because we do not have good heuristics for the LAP. At the other end, we have problem-specific end-to-end learning, where we completely replace a solver with a machine learning pipeline. In our case, we're somewhere in the middle. We use entropy, and so we are optimizing for simplicity and data efficiency. And so we integrate within the branch and bound framework. So we collect some information about the nodes that we visited, create a feature vector, feed that in the model, and from the prediction, we take an action which will guide the solver in the right direction through the callback and adding a lazy cut. So to give an idea, what we do is that we make a basic assumption that the solutions in the LP nodes that we visit are random variables. And then what we do is that we compute the entropy of different objects, like A and B. And here, the entropy of A is greater than entropy of B. What that means is that B is more stable than A. And therefore, what we can say is that there's less uncertainty associated with B. It's less risky to make an assumption about the solution of B. So the label here is the stability of solutions. So I put the definition of entropy here, minus B log P, but we don't predict the entropy. What we do is we convert that into a label, a binary label, which tells us if the solution is stable or unstable. And here I'm giving, and we do this by using a threshold. So in here in my data set, I give an example on a set of LLP instances. The median here is 0.22. And so all of the trains or objects that are below that threshold will be considered stable and all the other unstable. A machine learning model you use is a fast random forest, written in Julia. So compared to a deep learning model, we're less prone to overfitting. We have little tuning required. We have a small footprint. We do not require GPU, and we have a constant time update. So no batching is required. This is useful because branch and bound is sequential. So here is an accuracy over time on training on one instance. So we plateau around 90% accuracy here. And so next is the policy. So what type of actions we do. What we do is we basically add a lazy cut in the callback. We fix a certain binary variable to 1. We do this in 2 different ways, through a scoring policy that we call our threshold policy. Without going into many details, a scoring policy is more conservative, whereas the threshold policy is more aggressive. So here's the action accuracy for our policy. So we reach, in that example, 100% accuracy after 150 iterations. And on the right, we have the distribution over action accuracies for a set of instances, so between 80% and 100%. But we do not optimize for that. What we care about, in our case, is finding a good solution quicker. So we have two different ways of measuring it, the primal integral, so the area under the curve for the gap versus time graph. We also look at the interpolated speedup, which gives us an idea of how fast we can find a solution at a given gap. And so here's the results. So the PIR here is a primal integral ratio. So if we're below 1, it means we're better than the baseline. So we can see for the 3 policies that we tested, the body of the box plot is below 1. With TP is more aggressive, so we have more outliers here. We try on different instance sizes, medium, small, medium, and large. For both small and medium, we stayed below 1. However, for large instances, we have performance degradation. So this is to be expected because we train on one small instance, and therefore this is out of distribution generalization. And so this was expected. We also here a graph on the speed up. So for SP, we had up to 10x, whereas TP was up to 20x speed up. And we also, you see here, show the gap. So in all our 3 policies, we had a gap below 2%. So to conclude, we designed methodology with very low overhead, a small model and training set, and we demonstrated good performance on the LEP. So about up to 10x speed up with a gap below 2%. So next, we're looking at network design problems, which have a similar structure, where there's some set of binary variable, some set of continuous variable, and the goal is to predict the binary variable in order to speed up the process. So I hope you enjoy my presentation. Thank you for listening.